everyone. We're going to go through the 2024 physics exam. So I'm going to split this into parts and we'll just see how long each one goes. I'll do the multiple choice in this first part. It's a new style, so make sure you're familiar with just the layout and the new font and things based on this new study design compared to the old one. Nothing really new in terms of the information, just make sure you are used to how this looks compared to the last, I don't know what it was, 7-8 years of the previous study design. Let's get to it. Zoom in a little bit. Alright, for each question's worth 1 mark. You don't get minus marks for anything unless you just don't answer a question, then you'll get 0. If you're incorrect, you get 0. You don't have to show any working out in multiple choice, although there is plenty of space provided if you would like to. Question 1. Joe is standing inside a lift that is travelling vertically upwards at a constant speed of 2 meters per second as shown. Joe has a mass of 75 kilograms. Which one of the following is closest to the force exerted on Joe by the lift floor? So if you imagine Joe, she's got some forces acting on her. There's obviously gravity acting downwards, and there's the normal force of the floor acting upwards on her. And the fact that it says that she's moving at a constant speed means that all of the forces acting on Joe must sort of cancel each other out, right? Otherwise there'd be a non-zero net force on her and she'd be accelerating, not traveling at a constant speed. So we can deduce from this that the force exerted on Joe by the lift floor, okay, this one that we're interested in, force by the floor, must be equal to the force of gravity acting on Joe. So what's the force of gravity acting on Joe? That's just mg. Mass is 75 kilograms and g is, say, 9.8. I believe just quickly here, I believe the exam specifies in the, where am I going? Right at the end, in the data sheet to use 9.81, whereas previously I believe the exam just asked you to use 9.8. So just be careful with that. So I am going to include it here. I don't have my calculator on me, but we can kind of see that the answer is closest to 740 newtons. So we'll choose option C. Question 2. A space-based observatory of mass big M has a circular orbital radius big R around Earth. Modifications to the SBO have doubled its mass, but its orbital speed is kept constant. Which one of the following is closest to the orbital radius of the SBO after the modifications have been made? Okay, so going back to theory, if you go look at your equations, you'll notice that when an object is in orbit, its orbital velocity has nothing to do with its mass and everything to do with its orbital radius. So the fact that it's kept the same orbital speed, right, that must mean that the orbital radius must be the same as it was before as well. Okay, so we can, without any calculations at all, just say that the answer is B, original orbital radius. Alright, continuing down, question 3. The diagram below shows a small ball travelling at a constant speed on a horizontal circular path while suspended from the ceiling by a string, as shown in the diagram. Which one of the following best represents the force or forces acting on the ball as seen from a front-on view? So I guess from the view that we're kind of looking at it at the moment. Well, obviously if you're on Earth, which we assume we are, you're going to have the force of gravity acting downwards. And from this view, at least, there is one more force, which is the tension in the string, pulling the ball back up that way. Okay. Does it say anything about wind resistance or anything like that? No, it doesn't. I assume if it was in air, there would be some air resistance. But remember, air resistance points in the direction opposite to motion. And at that point in its motion, it's sort of coming out of the page, so the air resistance would be pointing back into the page, which we can't see if it's from a front-on view. So I guess that's the best we can do. And that's also what the question is asking for. Which one of the following best represents the forces? So those are the only two we can really see and really describe, so we're going to say that the answer is A. Alright, moving on. Question 4. The diagram below shows a 50-gram ball and a spring inside a horizontal launching tube. Assume that the launching tube is frictionless and the mass of the spring is negligible. A force versus compression graph for the spring is shown below. Consider the spring to be ideal. Alright, so whenever you've got a graph, first thing you should check are the units. So what are the units here? We've got newtons on the y-axis and centimeters on the x-axis. Now, with a force versus compression or a force versus extension graph, the sort of standard units that we should be using are newtons and meters. So this, we have to just have to make a note that if it's expressing everything in centimeters, then that's times 10 to the minus 2 meters, right? So when you use any numbers in a calculation, don't use the numbers that you see, use their sort of converted form back into meters, right? The spring is initially compressed by a distance of 10 centimeters with the ball in contact with the compressed spring. So you're sort of pushing the ball in, compressing the spring, and then a short time later the spring is released and the ball's going to pop out that way, I guess. Which of the following is closest to the speed of the ball as it leaves the tube? Okay, so it's giving us information about a ball and a compressed spring, and then it's somehow turning into a question about speed, so motion of the ball. So this is, I think, pretty clearly an energy question. So we're converting spring potential energy into kinetic energy. So first, let's just calculate the spring potential energy stored in the spring when it's compressed by 10 centimeters. And there are a number of ways to do this. The easiest way is to just look at the graph. And remember, a graph of force versus compression, the area under the graph will give you the spring potential energy when it's compressed up to that amount, all right? So when the ball's compressed by 10 centimeters, we're basically looking at all of this area in here, okay, up to 10 centimeters, right? Now that's just a triangle, okay? So the area of that is just half times base times height, so we can say that the spring potential energy is half times the base of that triangle, which is, it's not 10, it's 10 centimeters, which is 0.1 meters, right? Just be careful with the units. And half times base times the height of our triangle is 40. And that's in newtons, so we don't have to worry about changing that number. And we can work that out, and we end up getting 2 joules. Cool. So we know that when it's compressed, it stores 2 joules, and then assuming, there's no energy losses, all of that 2 joules of energy is going to be converted into kinetic energy when it's released. So now we just have to set up kinetic energy. So kinetic energy, we know has to be 2 joules, and we know kinetic energy is half times mv squared. The mass of the ball here being, where is it, 50 grams. Now just be careful again, that's going to be expressed in kilograms. So 50 grams is 0.05 kilograms. And so we can just sort of sub everything in and solve. So if I want to solve for V, I get V equals the square root of. Alright, so I'm going to take this 2, multiply it across, and we'll get 4, and then I'm going to divide by the mass. So it's going to be 4 divided by 0.05, and that's going to get us very close to 8.9 meters per second. Okay, so the only thing we need to worry about with those kinds of questions really are the units. Right, moving on. Question 5. A rock is dropped from rest at the top of a cliff towards the ocean as shown. Whee, all the way down. Which one of the following graphs best represents the rock's total energy as it falls towards the ocean from the top of the cliff? Ignore air resistance. Alright, so total energy. So the energy of an object has got to do with its kinetic energy, energy represented by, or not represented by, but energy associated with its motion, but also any potential energy, which is energy associated with its position. Now at the top of the cliff, it falls from rest because V equals 0, so it doesn't have any kinetic energy. It has a whole bunch of potential energy though. Okay? It's got a whole bunch of gravitational potential energy. We don't really know what it is, but we know that it's non-zero. Okay? As it falls, it simultaneously both loses gravitational potential energy because it's getting closer to, you know, your 0 point, which is sea level, but it's also speeding up, so it's gaining kinetic energy. And if we're ignoring air resistance or any other types of energy losses, then that total energy must remain the same throughout its motion. And so looking at all of our options, the only one that really fits that description is A, this sort of constant graph. Okay. If there was air resistance, could you think what would happen to the total energy of the rock? Leave your answer in the comments if you think you can answer that question. Right, question 6. So two magnets are placed as shown in the diagram below. The magnets are identical and point X is exactly halfway between the two S poles. Which one of the following best describes the strength of the magnetic field at point X? So point X is right in between two south poles. Well, you just have to kind of know this from theory that, you know, if you're equidistant from two identical south poles of two identical magnets, the magnetic field at that point right in the middle just cancels out, right? And there's a reason for that. I mean, if you imagine, say, from the left-hand magnet, the field from that magnet at point X, well, field goes into the south pole. So at point X, the magnetic field sort of vector would look like that. But also from the magnet on the right, the field from its south pole would point directly to the right. And so those two vectors cancel each other out, and so overall you don't have any magnetic field at that point X. So we can say it's very close to 0, if not 0 exactly. Question 7. Diagram A shows a single loop of wire carrying a current I within a uniform magnetic field. Diagram B shows the same loop rotated clockwise through 90 degrees. So you've just got a loop of wire, and I guess you can sort of say that it's rotating clockwise about this axis, okay, and it's just 90 degrees later it looks like that. Alright, the magnitude of the force F on side PQ and the magnitude of the torque on the loop in diagram diagram B compared to those in diagram A. Which one of the following rows in the table best describes a comparison? Alright, so let's think what's going on here. We've got two things that it's sort of asking us about: the force on the side PQ and the torque on the loop in total, right? Not the torque on the side PQ, just the torque on the loop. Let's think about the forces. What's going on with the forces in between the two questions? Well, you've got a current, okay, going this way, and that current is sitting in a magnetic field pointing to the right. Now we know from theory that we can use our right hand slap rule to determine the force on that part of the wire, okay, the force on that current. So if you imagine sticking your thumb, use your right hand, stick your thumb sort of into the page, stick your fingers to the right, your palm should be facing downwards. So what we're saying is that the force on this PQ, at least in the first position, is down, okay? that's force in diagram A. But also in diagram B, nothing's really changed. The position of the wire has changed, but the direction of the current is still the same. So you use the right-hand slap rule again, and it should tell you, again, that the force on this current is downwards. Okay? And because the current hasn't changed and the magnetic field strength hasn't changed, then the force will not have changed. So we can immediately eliminate B and C, because they say that the forces are different in each situation. So it's either A or D. Now A says that the torques are equal, D says that torque in position A is greater than in position B. So let's just think about which one that would be. So if you imagine the forces, now when we're talking about torque, you've got to think about the forces causing rotations, right? So imagine the other side of the loop. Okay, I'll just call it PQ, what have we got, R and S. Okay, so in diagram A, the current would be coming this way, right? And so you'd use your right hand slap rule again, but this time your thumb would sort of be pointing back towards you out of the page. Your fingers would be pointing to the right still, and your palm would be facing upwards. So on that side of the loop, the force would be pointing upwards, and that's good because that's going to cause the loop to rotate, and so it rotates clockwise, and that's why it does rotate clockwise to this position B. But imagine that the current's still going this way in diagram B. It's going to go up here, and it's going to go this way. So the current on the other side of the loop is that way. And again, using your right hand slap rule, you can see that the force is going to be upwards. Now we come into a problem because we've got two forces that are sort of opposing each other. That's going to sort of hinder the rotation of this coil. So imagine you've just got like a square coil and you're sort of pulling up on one side, pulling down on one side. It's not going to go anywhere. Okay, so there is no torque basically. And so we can say now that the torque in position A must be greater than in position B. So, oops, I'm going to say the answer is D. Let's go to the next one, question 8. So a straight wire P, 4 centimeters long and carrying a current of 5 amps is completely placed in a uniform magnetic field of magnitude 2 times 10 to the minus 3 Tesla as shown below. Which one of the following is closest to the magnitude of the force acting on the 4 centimeter long wire in the magnetic field? So we've got a straightforward equation to deal with this, which is F equals NBIL. You might have the letters in a different order, doesn't really matter. N is the number of wires in a bundle. This is just one wire, so that's 1. B is the magnetic field strength. In this case, 2 times 10 to the minus 3. I is the current in amps, 5, and L is the length of wire that is in the field. In this case it's 4 centimeters, but we've got to put everything in SI units, so meters. 4 centimeters is 0.04 meters. And just chuck that on a calculator, and you're going to end up with about 4 times 10 to the minus 4 newtons, which corresponds here to option C. Okay, so that's just a straightforward plug into an equation question. Question 9. Two equal positive electric charges separated by a distance d exert a force F on each other. The distance is changed so that the two charges now exert a force of 6F on each other. Which one of the following is closest to the new distance between the charges? Okay, so if the charges themselves do not change, alright, but the distance is changing, and we know that the force increases to 6 times its original amount, it must be that the charges have been brought closer together, right? And that kind of makes sense because the closer charges are, the stronger the force is between them. And all the options anyway say that the distance is smaller than its original, so that's fine. But the question is, what is that distance? So the way that I think about this is I say, okay, I have my original force F, I want a new force of 6F, okay? Now force, when we're dealing with electric charges, that is proportional to 1 over their separation, which in this case we'll call d, squared. Okay, so we somehow have to change this value d to something else so that when I simplify this fraction as a whole, I end up getting 6 times this original 1 over d squared. So what do I mean by that? So that means 6f is going to be, we're going to have to change the distance to something else, which I'll call 1 over, I don't know, what can I call that? 1 over k. Let's just call it k. So distance, instead of d, is now some multiple of d, all right? Because all our answers are in multiples of d, okay? And if I sort of take that k out of this square and also out of the fraction, I end up getting 1 over k squared times 1 over d squared, okay? Now it's this 1 over d that I'm interested in. That is our original force F, right? That comes from over here. So we know that this factor 1 over k squared must be equal to 6, because it's got to be 6 times the original force F. So really we're just solving for k here. K, if you just do some rearranging, k equals the square root of 1 over, it wouldn't be this, well, it would be, but I'll just do 1 over the square root of 6. Okay, and if you type that on a calculator, I'll do it very quickly. 1 over root 6, oops, not 1 minus, 1 over root 6, 0.41. Okay, so that means my answer is option B. Okay, yeah, so that's how I would go about doing it. There are other ways. You could just, I mean, if you don't really understand what's going on there, you could just make up some numbers for the charges, make up a number for the original distance, just call everything 1 to begin with, and then just substitute those new values in to your to your Coulomb force equation. F equals Q1 Q2 over R squared. Don't forget your K. Oh, I shouldn't have used K in the example, but this K is not Coulomb's constant, okay? It's just a placeholder. Alright, so if you don't know what I did, just make up some numbers for your charges, make up a number for the distance, and just plug each of these new distances into the formula and see which one spits out 6. Right? Okay, moving on. Question 10. The graph below shows the induced current through a coil of conducting wire as a function of time. So we've got a current, it's non-zero, but it's low, then it jumps up to a high current and then a low current. Alright, fine. Which one of the following magnetic flux graphs corresponds to the graph of the induced current as shown above? Okay, so there's a current in some kind of coil, which means there must be some EMF driving that current. Okay, so we could, instead of using the words induced current, we could also just use the word EMF, or the initialism EMF. Alright, so just pretend that this is an EMF, EMF versus time graph. And we know from theory that if you want to get an EMF versus time graph, you need to look at the gradients at various places on a flux versus time graph. Okay? And so what's basically happening here is that our corresponding flux graph is going to have a non-zero gradient for this portion of time, a larger non-zero gradient for this portion of time, and then go back to the original smaller non-zero gradient for this portion of time. Okay? If the gradient is 0, then that means the EMF is 0, and thus the induced current would be 0. So again, looking at the gradients of our magnetic flux graph, it can't be this one because the gradient at this portion here is 0, which means the EMF induced during that period of time would be here, 0, or here on our original graph. Okay, that's not what's happening. Same with this one, the gradient's 0, so the EMF would have a value of 0. Okay, so we can eliminate A and B. C is the most likely candidate, and the answer is actually C, so I'll just highlight that, but we'll point out why it's not D. So D has a period of time where your gradient is 0, okay, and that would correspond to an EMF value of 0. And it is true that the EMFs in this period of time here and here have non-zero gradients. What would happen is that your induced current would have a value of some positive number here, but some negative number for this period of time, and that does not match our original graph. So the only one that matches the best would be option C. Okay, so non-zero gradients for each of these portions correspond to non-zero EMF values, or non-zero induced current values for each of those portions of time. Okay, and you can see this gradient here is roughly equal to this gradient here, which means that the EMFs, or the induced current, should have the same values for those periods of time, which they do. And this has a slightly steeper, larger gradient, so that means the induced EMF and current would be larger, and have a larger value in that period of time. So option C is the correct one there. Question 11. In Victoria, the electrical energy generated at the Loy Yang A power station is transmitted to Melbourne, approximately 170 kilometres away, using 500 kilovolt transmission lines. Which one of the following best describes the reason for the use of high voltage transmission of electrical energy over long distances? Okay, best describes. Okay, you might have your own wording of how you would explain to someone why we should use high voltage transmission. I mean, if we're looking for the best answer, probably the best thing to do is just look through each of the options and try and pick which one makes the most sense. A, transformers can be used to increase the voltage. That's not a reason for why we use high voltage. That's just a statement saying transformers can be used to increase voltage. That's not why we do it. So it's not A. B, high voltages reduce energy losses in the transmission lines. And that is indeed true. So we'll sort of put our finger on that one for now. C, high voltages can easily carry the large power required by cities. I mean, high voltage doesn't necessarily mean it's going to carry a large amount of power. I mean, it certainly helps, but you could have an extremely large current and a low voltage, and that's still going to give you a high power, so that's not necessarily the best answer. Or part D, high voltages reduce the overall total resistance in the transmission lines. Well, that's just false. The resistance is a factor of the material used in your transmission lines, and also the total length of those transmission lines. So it's not going to be D. So B seems to be the best option there, right? It is used to reduce energy losses in transmission lines. We don't use high voltage. I mean, if high voltage is I would say high voltage is a side effect or a byproduct of what's going on when we transform our electrical power to do this long distance transmission. The reason why we transform it is to transform the current. We want the current to be smaller, but in order to keep the power the same, if you're making current smaller, then voltage must increase. So we don't use high voltage. High voltage, I would say, is a byproduct of the transformation process. But correct me if I'm wrong. That's just how I think about it. All right, moving on. Question 12. So the diagram below shows a coil moving upwards from the north pole of a stationary bar magnet. Which one of the following correctly identifies both the direction of the induced current as observed from the top of the coil, so where this I is, and the direction of the magnetic field produced by the induced current inside the coil as observed from the side of the coil? That's a really annoying question because we've got two perspectives involved here. So imagine you've got two eyes, or two people. One's looking down there, okay, and there's another person just looking from this direction, okay. All right. So let's look at the current direction from this eye. Okay, so there's a coil here, and we want to think what direction the current's going to be what direction the current's going to be going according to this person's eye here. So we're moving a coil away from a magnet. So the magnet has magnetic field pointing upwards at the moment. Okay. And we are moving the coil away from that magnet. So the flux through the coil is decreasing. Okay, the flux through the coil is decreasing. Now, Lenz's law states that a current will be induced in a coil so as to oppose any change in flux through that coil. Okay. Now, the way that I like to think about it is there's too much stuff to write down, but in my other notes and other videos that I've done, I would say that, so ask yourself this question: is the flux increasing or decreasing in this scenario? And we know it's decreasing. Okay. So what I would say, if it's decreasing, stick your thumb in the opposite direction of the flux. Okay. So your right hand, take your right hand. The flux right now is upwards, so you imagine your thumb's upwards, but you're decreasing the flux. So just flip your hand upside down. Your thumb should be pointing down. Okay. Lenz's law states that the induced current in this coil will oppose this change in flux. So the change in flux is downwards because it's decreasing, and the original flux is upwards. So to oppose that, you flip your hand back the right way up, so your thumb's pointing upwards again. Okay, that's the critical step of Lenz's law, is that the current opposes the change in flux. Okay, change in flux was down, that's why I point my thumb down. We're opposing that change in flux, so now you flip your hand around, now your thumb's pointing back upwards. And what are your fingers doing from your point of view, from that eyeball? Your fingers are curling around in an anti-clockwise direction. Okay? If you're stuck on Lenz's law and you're trying to figure that stuff out, go back and look at your notes. Go ask your teacher, all right? I've got a very specific method of working it out, and it works every time. It just takes a while to get used to, okay? But change in flux is downwards, opposing that is upwards, and from the perspective of that eye on the top, your fingers would be curling anti-clockwise, okay? So it's either C or D. Now, according to this eye, which direction is the induced magnetic field? Induced magnetic field, well, that's the sort of second step in Lenz's law where you oppose that change in flux, so you flip your hand back the other way. And that is now pointing upwards. Okay, my thumb would be pointing upwards according to this observer here. Okay, and so I can say that the answer is C. And it's all just to do with using your Lenz law and your right hand grip rule. Okay, this can be one of the more trickier things about physics, about the electricity section, so go back and study if you need to. Question 13. The diagram below shows a simple generator made from a loop of wire, a commutator, and magnets. A mechanical energy source rotates the loop smoothly, so someone could just be turning it around. The magnetic field is constant and uniform. The output is displayed on an oscilloscope. Which one of the following best describes the output that will be observed on the oscilloscope? Okay, so it specifies that there's a commutator. Okay, and that's this thing here. And we are turning the loop ourselves. Okay, it's not a motor. Okay, there's no current in there initially. We turn this coil, this loop ourselves. And in doing so, we are then changing the flux through the loop at various points. And because we're changing the flux through the loop, we're also going to be inducing a current in that loop. Okay, that's just Lenz's law at work again. All right. So we're inducing a current, and every sort of 180 degrees, that current swaps direction because of the orientation of the loop inside the magnets. So normally what you would see, if you could attach sort of an oscilloscope directly to the loop, you would see something that looks like this. Okay, an alternating current because the loop is constantly turning, and opposite sides are then alternating their direction of motion through that magnetic field. So you end up with this alternating current. But because of the DC commutator, basically what happens is these bits underneath, these negative currents, if you will, they would flip back up and become positive again. I'm not going into the theory, we're not doing a theory lesson, this is just going through the exam questions, okay? So it's going to be a DC graph, these bottom parts don't count anymore. It's not a constant DC graph, it is a varying valued DC graph. So we can say that the answer is A. Alright, question 14. A rocket passes a space station at a horizontal speed of 0.85 c parallel to the side of the space station. There's a circular window on the space station as shown in the diagram below. Alright, cool. Really basic diagram there. The person inside the passing rocket observes and measures the window of the space station. Which one of the following statements best describes the measurements taken of the window of the space station? Okay, so there's a person in this rocket and they're going past a space station in this direction, okay, relative to this window. Again, this is just straight from the theory. If you look at the way that the answers are worded, they're talking about the dimensions of the window, basically. How would the window look compared to when observed by this person in the rocket? Now, again, straight from theory, we're going to be dealing with a length contraction situation here. And just remember that length contraction is only applied in the dimension that is parallel to the relative velocity. Okay, so if you're traveling in this dimension this way, okay, then the window is going to contract along this axis. And so it's going to end up looking more oval shaped like this. The vertical distance does not change because there's no component of motion in that vertical direction. It's going purely horizontal, so only the horizontal distance contracts. Okay, and the answer that best fits that is option D. Okay, the horizontal measurement will be less than the actual window, but the vertical measurement will be the same as the actual window. Hope that makes sense. Go back to your theory. Question 15. At the Australian synchrotron, electrons are accelerated to close the speed of light c by the linear accelerator. Consider electrons that enter the Australian synchrotron booster ring with a Lorentz factor of 200, and as a result of further acceleration in that ring, reach a much higher value with a Lorentz factor of 2000. Which one of the following best describes the effect of the booster ring on each electron's speed and energy? Okay, so I guess I don't know, like who's teaching you or the way that you get taught these things, but the closer you are to the speed of light, the more energy is required to fractionally increase your speed. Okay, so let's say you're going how can I phrase this? All right. Let's say you want to increase your speed by an extra, say, 5% from your previous speed. Okay, closer to actually that doesn't make any sense. Let me start again. Okay, let's say you're like nowhere near the speed of light. All right, you're going 5 meters per second. Okay, if you want to increase your speed to 10 meters per second, you need to have an additional 5 meters per second kinetic energy's worth, I guess you can say, of energy inputting into your system to increase your speed to that amount. So you're kind of doubling your energy at that point. But the closer and closer that you get to the speed of light, if you just keep doubling the energy, you're not going to always be doubling your speed. The amount of speed that you increase by will decrease over time, right? So if you keep doubling your energy, you're not going to, say, add an additional 5 meters per second to your speed. Eventually that'll start decreasing. You might only be adding 4.9, 4.5, 4 meters per second, all right? And the closer and closer you get to the speed of light, if you double the energy, you don't double your previous speed. That fractional increase gets smaller and smaller as the closer you get to the speed of light. Okay, so the electron's speed will increase, but only by a small amount. Okay, but the amount of energy required to produce that increase would be a large amount. Okay, so I would say that the closest, best answer to what's going on here is answer B. Okay, I hope that explanation makes sense. I'm sure there's another way that we can show this with various equations and things like that, but this is only multiple choice. You're not supposed to be doing sort of like a huge deep dive into physics and deriving things. You're sort of just using your surface to mid-level layers of knowledge about your physics course to answer these questions quite quickly. Remember, you only get about a minute per mark, really, to figure out what the answer to these questions are, okay? And hopefully, I guess, that this fact is being taught to you or explained to you, okay? All right, so again, the closer you are to the speed of light, the more energy is required to produce the same increases in speed. I hope that makes sense. Okay, so if you want to increase your speed, you need a large amount of energy, but it's going to get harder and harder to do that using the same amount of energy the closer you get to the speed of light. Question 16. Diagram P shows 5 energy levels of an atom with 5 transitions indicated. Diagram Q shows 4 possible sets of spectral frequency lines. Okay, so this is your, I guess, maybe what would be emission spectrums. Which one of the frequency spectra shown in diagram Q best corresponds to the transitions shown in diagram P? So I look at this and I say, okay, there are the longer arrows means higher energy or higher frequency transitions. Okay, remember the energy of a transition is tied up to the frequency of the photon that is released in that emission, right? So there are 3 that I would classify as high energy or high frequency emissions, and so I'm looking for these diagrams on this side who have 3 lines sort of towards the high end of that diagram, and they really are only that option and that option. The other 2 only has, well, this only has a 1 on the high end, and this, you might say, only has 2 on the high end. So we're going to discount options A and C. I would probably say these are closer together than further apart. So I'm looking at B and saying, okay, these 2 lines, they're too far apart for me to comfortably say that that's where they should go. Okay, to me, these 2 lines here, they're low energy transitions, okay, which correspond to low frequencies. So they should be closer together in the spectral diagram. So I'm going to go with D here. And that is indeed the answer if you go look at the examiner's report. Okay. Oh, I should highlight there. Okay. Nearly done. Question 17. The diagram below shows a standing wave on a stretched string between 2 fixed ends at time t equals 0. The frequency of vibration of the string is 50 Hertz. Which of the following diagrams correctly shows the position of the string at time t equals 0.01 seconds? Alright, so we need to figure out the frequency of this, sorry, not the frequency, I guess the period of this standing wave. And we know that in one period it's going to return to this exact shape. Okay, half a period later it will be inverted and it will look like this, and at a quarter of a period and 3/4 of a period it will just be completely flat and 0. Okay, so the question is, what is this? How does this fit in? Is that a quarter of a period, half a period, a full period? What is it? So to work out the period, if you've got a frequency, period is just 1 over frequency, in this case 1 over 50. 1 over 50 is 0.02. So the period is 0.02 seconds, but it's asking what does the shape of the wave look like at 0.01 seconds, which is half a period. Okay, and I said half a period later, you're going to get a graph that is inverted to the original waveform, I guess you could say. So I'm going with option B. Okay. Question 18. An interference pattern produced by monochromatic light is viewed on a screen placed at distance L from a double slit system with a slit separation D. The distance between the centers of 2 adjacent bright bands is delta X. Okay, so there's your distance to the screen L, the slits D apart, and adjacent bright bands are delta x apart. The distance L is doubled and the slit separation D is halved. Which one of the following is closest to the new distance between the centers of two adjacent bright bands? Okay, so there's a formula governing all of this. So the formula, which is in your formula sheet, excuse me, is delta x equals to lambda L over D. Lambda is just the wavelength coming from the laser, wavelength of the light, and everything else is what it says it is here. So if I double L, okay, I get lambda times 2L, but I'm also halving D. So I'm going to put that over half D. And what do I get if I pull those numbers out and try and revert to my original form? Well, 2 divided by a half is 4. So combining those two numbers, I get 4 times lambda L over D. Now lambda L over D was our original delta x, but after doing these transformations, I guess you could call them, we end up with 4 times that. Okay, so my slit separation, not my slit separation, my bright band separation is now 4 times what it originally was. So I'm going to go with option D. Penultimate question for our multiple choice section, question 19. The orbital velocity v of a satellite in an orbital radius r around a planet of mass m is given by this equation here. Sure. Which one of the following linear graphs is consistent with this relationship? Okay, so this is a really nice question because it gets you to hopefully use a skill that you would have learned when doing your investigation, which is linearizing data to prove that your data fits a certain relationship of some kind. Okay, basically we want our equation to be of the form y equals mx. Okay, your y variable is whatever goes on the vertical axis and your x variable is whatever goes on the horizontal axis, and m is just some constant number consisting of constant values. So that's not what we have here because there's a square root over this r, and also the r is in the denominator of a fraction. We need it to be sort of in a numerator of a fraction. So what I can do is rewrite this as v squared equals gm over r, okay? But I could also write this as gm times 1 over r, okay? And if I just call 1 over r, I just give it a new name and I call it x, and I give v squared a new name and I call it y, and I give gm a new name and I call it m, then we're in the required form to produce a linear graph. Okay, but what is y? Y is our vertical axis, and y we've said is the name of v squared. So we know v squared is going to have to go on our vertical axis, and our horizontal axis, well, we've given x the name to 1 over r. So 1 over r has to go on our horizontal axis. So the only thing that matches that description is option D there. Okay, so this is called linearizing your data, or linearizing your graph or formula or whatever you want to call it. Hopefully that makes sense. If it doesn't, go back and ask your teacher or look at your notes. Question 20, data can be described as precise when. This should just be somewhere written down on your cheat sheet. It's just the definition of precise data. You should have a definition of precise data and a definition of accurate data. Okay, precise data, simply just from the definition, is when you repeat an experiment, your data that you collect doesn't change very much. Okay, that is why we repeat trials, so that we can get data that we know is consistent and precise. Okay, if your data's all over the place, it's not very precise, are you? Imagine throwing darts at a dartboard. You want to always be aiming for the same spot, okay? But if you're aiming for the same spot, but you're all over the place, you're not very precise, okay? All right, now you might not be aiming at the right spot, but you should be aiming for a spot and hitting that spot consistently. That's what precise means. The other word, accurate, is when you are trying to aim for a spot and you get that spot, or at least your average results sort of average around that spot that you are trying to hit. Okay, very good analogy with the dartboard. There's pictures online. Go have a look. But otherwise, this comes straight from the definition, straight from the study design, almost straight from the VCAR website, pretty much. Okay, so we'll stop there and we'll come back and we'll do section B.